Welcome. This video is going to go through phase change in energy, kinetic molecular theory, and sublimation. So starting with the idea of, in order to understand phase change in energy, you have to have an idea of what a temperature is. A temperature is a measurement of the energy of a system or matter. It's also defined as it's a measurement of how much molecules are in motion. The more these molecules are moving around down here, crashing into the thermometer, the more the thermometer will warm up and expand and register more temperature. If at the same time, saying it similarly, if you lower the amount of energy they have, slowing them down, the molecules in the thermometer will also slow down and the temperature will go down. So the first thing you have to understand is a phase change graph. This is supposed to be a phase change graph for water, where you have temperature on the y-axis and time, or the amount of energy, on the x-axis. So just kind of building it, the way that you should know is, first you got to recognize is the freezing point of water is right here on this flat spot. The boiling point of water is here. And so in this area below 0 degrees is where you have water as a solid. Between these two spots, the 0 and 100 degrees, where water exists as a liquid, and above 100 it exists as a gas. And the points where you have one state of matter changing into another is called a phase change. So solid to liquid is a phase change, liquid to gas is a phase change. And the points where they change have names too. So solid to liquid phase change is called the melting point. Liquid to a gas phase change is called the boiling point. And so 100 degrees is the boiling temperature. 0 degrees is the melting temperature for ice. Last little details on the phase change graph. When you cool something down back to its boiling temperature, it's called a condensation point, when a gas cools back into a liquid. Or if you have a liquid cooling back into a solid, the temperature at which that happens is the freezing point. Notice the condensation point and the freezing points are the same as the melting and boiling temperatures. Evaporation of water can actually occur along this line here at pretty much. So going on a little further here, one of the things you have to notice in the phase change graph is that when matter is going through the phase change, the temperature of that matter doesn't heat up. What I mean by that, for example, is ice doesn't get any warmer than 0 degrees Celsius. And the answer is, why does that happen? It's because any energy absorbed by the ice in the solid state actually causes those little water molecules to go from a solid to a liquid. So they turn into a liquid, and the remaining ice is still in the original state. So because any energy absorbed goes through the state change. So extra energy absorbed by the ice ends up melting it, but the remaining ice stays below 0 degrees. If you add some more heat energy, any water molecules of the ice that reach molecular motion of 0 degrees will actually come off and turn into water. The remaining haven't got there yet. The same thing happens in boiling. When you boil water, if this was boiling right here, any water molecule that absorbs a little bit more heat energy at 100 degrees Celsius, it's going to break free and it's going to float away as a gas. The remaining guys haven't got to that temperature yet, so they're still there at 100 degrees Celsius. And it's not just water that goes through this. All types of matter have similar phase changes. Again, I could take solid gold and melt it into liquid gold. The melting temperature, whatever the melting temperature of solid gold is probably like 2,000 degrees Celsius. It would never get above that, because any gold molecules or gold atoms that absorbed more energy would turn into a liquid. The remaining gold would still be below that actual melting temperature, whatever it happens to be for gold. So again, just another look at the phase change graph, and we're talking about these flat spots. So when a solid is changing into a liquid, the solid never heats above its melting point. Any molecule that gets enough energy to be above its melting point is a liquid. Same as a liquid. Liquid water, we did this in class, never rises above 100 degrees Celsius, because any water molecule that absorbs more energy than is measured as 100 degrees turns into a gas. The remaining ones are still at or below 100. So another topic within this is the role of salt that we did in the ice cream lab, and how it's used to actually melt streets. So here's the answer, basically, of what you need to know for that. Is adding salt changes the physical property of water. It lowers the freezing point from, normal water has a freezing point of 0 degrees, and depending on the type of salt you add, you can lower water's freezing point to as low as 21 degrees Celsius. Mind blower for Bill Nye there. But why does that actually happen? What does the salt do? Well, there's two parts written in here that the salt does. One, I'm going to start here. Salt gets in the way of water refreezing, and salt also helps stick to the ice and water molecules and pulling them off. So here's a couple pictures to explain that. One, the second part here, gets in the way of freezing. If you read this, it'll help too. But at the surface of an ice, there's always water molecules that are moving into the liquid phase, coming off, refreezing, coming off, refreezing. When there's no salt around, they can refreeze at 0 degrees. There's no problem. If you add salt, which is supposed to be these little yellow dots here, when they come off and try to refreeze, well, a lot of times there's salt molecules in the way because the salt likes to stick to the water. And so in order to get, say, this little water molecule to refreeze again, you have to slow things down even more to a lower temperature, a new melting point and freezing point, because of the factor that the salt is in the way there and blocking the water molecules from refreezing. The second part of this statement here, salt sticks to the ice and pulls the water off. Water, we learned, has little tiny positive and negative charges on it, partials we call them. And salts, sodium chloride, also have positive and negative. So they're attracted to the water molecules in the ice. So not only are they blocking the way, as this picture shows, they can also stick, as is going on right here, to the water molecules and help pull them off. And once they're off, the salt can also stick to the water molecules, preventing them from sticking back as a solid. Going on here. So ultimately what happens when you add salt, changing the physical property of water, its normal melting point, the ice can't maintain its crystal solid structure and it melts. The other trick within this is, in order to melt, to break off a water molecule from the other water molecules, it actually has to take in heat to break from the solid to the liquid, which of course you know, in order to change a solid to a liquid, you have to add heat. Well, that heat comes from the surroundings. And when you have the salt there, it kind of speeds up the process of the ice absorbing heat from the surrounding, which is why when we did our ice cream lab, the solution with the salt and the water together helped pull more heat from the milk and made the milk freeze versus just when we had the ice melting on its own. Just one other little tangent here, thinking if you have a really cold night on the road, if it goes below 21 degrees Celsius at night, of course the road can refreeze. You just got to get cold enough, and even though salt can change the melting point, you can get to the point where that water ends up freezing itself. So another question that we answered in the phase change has to do with boiling points. We say the water's boiling point is 100 degrees Celsius. But in Denver, and as we saw in the lab, it's not exactly that. And this 100 degrees Celsius boiling point comes from water boiling at sea level. This little chart here shows that if you measure the boiling point of water at sea level, you get 100 degrees Celsius. But as you climb up in altitude, so 6,000 feet, it only boils at 93. 10,000 feet, only 90. 20,000 feet, only 79. As you climb in altitude, the boiling point goes down. And that has to do with the amount of atmospheric pressure pushing down on top of the water. Backing up here a second. So in Denver, we should have got in the water lab where we were melting ice and boiling the water, that the water boiled at about 95 degrees Celsius, which a lot of you guys did. Some of you guys got 100, some of you guys got different degrees, and some of that can be explained by the thermometers that we use that maybe aren't as accurate as they could be. And dirty glassware actually will also make the boiling point higher than normal. But so why does altitude matter? So what's going on here that's changing the boiling point? What you have to appreciate is that if you were standing down here on the ground, all these little air molecules, gas molecules are on top of you, and gravity's pulling them all down on top of your head. That's creating a pressure. At sea level, for every 1 square inch, you have 14.7 pounds of pressure on your body. 18,000 feet, it's almost half that for the same volume of air pushing down on you. Well, when you have air pushing down on top of a liquid, like a glass of water, it takes more energy for that water to break free and turn into a gas. When you have less pressure pushing on top of it, like if you were up here with a glass of water, the water can leave into the gas phase a lot easier. So you have to put less heat energy in it, and thus the temperature will actually be lower when it boils. We showed this video here that if you go in space and you have no pressure on the water, the water will actually boil immediately at like 21 degrees Celsius room temperature because it doesn't take very much energy for it to break free from the rest of the water and turn it into a gas. So atmospheric pressure changes the boiling point. When you have less pressure, lower pressure at higher altitudes, you have a lower boiling point. When you have more pressure at lower altitudes, it takes more energy into it to reach the boiling point, to break free and turn into a gas. So what we've been learning about with the phase change here and our states of matter is actually called kinetic molecular theory. You'll remember in class that we had the two beakers with food coloring in them. The only difference between them being one was really hot, the other was really cool, and the food coloring spread out faster in the hot one versus the slow one. Well, that was a demonstration of kinetic molecular theory, which basically states that the more energy a set of matter has, the more in motion its molecules are. And it relates to what we learned about solids, liquid, gases, and plasma. The more energy you have, the more the molecules are going to be in motion, and the more likely they are to change phase. Which we said that. The kinetic part of the kinetic molecular theory comes from, or has the meaning that kinetic means caused by motion, relates to motion here. So when we say it's a theory, we have a lot of evidence that molecules are in motion, which is where this piece comes from. So it's a theory about molecules moving is kind of how kinetic comes into kinetic molecular theory. Parts of the theory that you have to know, just in quick summary, is that all matter is made up of tiny particles that are in constant motion, and that particle motion is dependent on temperature, or the amount of energy they have. The more energy they have or temperature, the more motion you get. And this also results in heat transfer between things. If you have two things next to each other of different temperatures, one, because of the motion of one sample, it can actually excite the crash into and cause more motion in the molecules of the other sample, increasing its temperature, transferring its energy, or transferring it between two items. The last physical property we studied in the unit is sublimation, which here's a picture of dry ice or carbon dioxide going through sublimation. And the big question of what is dry ice, first of all, you have to know it's frozen carbon dioxide, so it's solid carbon dioxide. Dry ice seems crazy, but it has a boiling point, not a melting point, a boiling point of negative 78.5 degrees Celsius. So we only find carbon dioxide naturally here on the Earth as a gas because it boils at negative 78. There's no place on the Earth where it could be cool enough for carbon dioxide to form a solid. Well, this comes up with this idea of sublimation, this term. So what happens if you have dry ice that's man-made from a factory? You can even buy this at King Supers, as we saw in class. So you have that solid dry ice that looks like this. You put it in the air. Our air, 20 degrees Celsius, is way hotter than its actual boiling point. So what happens is the carbon dioxide at the surface of the solid gets warmed up so fast, it skips the liquid stage and goes directly to a gas. That's what sublimation is, moving directly from a solid to a gas phase. There's no liquid phase. And the reason why that happens again is because the temperature difference between the boiling point of whatever that substance is and the actual temperature of the air around it, it just heats right up into a gas. There's no time to be a liquid. And other substances, not just carbon dioxide, can go through sublimation. So take, for example, you never see solid oxygen because its boiling point is negative 183 degrees Celsius. But if you can get liquid oxygen or even go down to a solid. Same thing would happen, though, because it's such a negative temperature that it turns into a gas at. This is its boiling temperature. It would immediately, if we cooled it down to a solid, sublimate into a gas. Same with hydrogen gas. It has a boiling point of negative 423 degrees Celsius. You could even get water to sublimate if you did, if you took an ice cube, say this was an ice cube right here in this picture, and I had maybe a flamethrower and I just threw a whole bunch of fire at this thing, increasing the temperature around the ice so high the ice would go from a solid directly to a gas. It's going to absorb so much energy, it's not going to have to spend any time as a water. So water can sublimate as well. It just has to be right. right conditions. The conditions on Earth normally don't have water sublimate because the three phases of water, the boiling point and the melting points, are all around normal Earth conditions. But for these other materials here, you get sublimation because their boiling points are so low. So last slide here is just summarizing some of the physical properties that we've studied at the last part of the unit here. Make sure you pay attention to weight versus mass. Mass is the amount of matter in an object. Weight is, it says changes on different planets, but this is also measurement of the gravity's pull on an object. Volume, the amount of space filled by an object. Density stays the same unless you change the temperature. And then sublimation, a summary. State change from a solid to a gas is caused from the boiling or melting point of a substance being very low. If they're very low, you get sublimation. And then other physical properties that we've kind of looked at throughout this unit. And that's it. Good luck on the test.